our fastest supercomputers, which is exciting for us because we design and build quantum computers to tackle precisely this kind of seemingly impossible challenge.
In a world where computational power is king and technology reigns supreme, IBM is no stranger to pushing boundaries and defying expectations. The technological titan has consistently been a trailblazer, leading the charge in advancements that continue to shape and redefine the landscape of computer science. But this time IBM has surpassed even its own lofty standards with a monumental leap that promises to revolutionize the industry. The future has arrived, and it's quantum. Imagine a computer so powerful it can simulate novel materials to sequester carbon from our atmosphere, develop low-cost fertilizers that save both energy and fossil fuels, and solve problems so intricate that conventional supercomputers falter under their weight. It seems a fantasy and ambitious dream from a sci-fi novel, but IBM has brought this vision into the realms of reality. The quantum-centric supercomputer, a breathtaking testament to human ingenuity, is poised to redefine our understanding of computing power. The astounding 100,000-qubit quantum-centric supercomputer IBM has proposed is not just a paradigm shift, it's a seismic event, a quantum quake that sends shockwaves through the industry, challenging our understanding of what's possible. And this isn't a mere step forward, it's a quantum leap into an exhilarating new era of computational power. We aren't just walking into the future, we're hurtling towards it at warp speed, holding our breath as the world around us transforms before our eyes. The power of this machine is unparalleled, harnessing the fundamental principles of quantum mechanics to solve problems that were previously thought to be beyond our reach. This is not just an evolutionary step, it's a revolutionary change. We are standing on the precipice of a new era where quantum mechanics and computer science meld into an uncharted frontier of technological possibility. The quantum-centric supercomputer is the brainchild of this audacious vision, a vision that refuses to be bound by the constraints of classical computing, a vision that challenges the very laws of physics. This system is slated to usher in an era of quantum-centric supercomputing by 2033, aiming to tackle the world's most complex and pressing issues. It represents the zenith of computational innovation as it seamlessly integrates quantum and classical power, akin to how today's computers blend CPUs and GPUs. The 100,000-qubit quantum-centric supercomputer is not just a groundbreaking innovation, it's a symbol of human resilience, a testament to our ability to dream, innovate, and conquer even the most daunting challenges. What we're witnessing is more than a technological milestone, it's a monumental stride in humanity's endless pursuit of knowledge and power. This is about more than just technology, it's about the limitless potential of the human spirit to innovate, adapt, and overcome. It's about our ceaseless quest to push boundaries, to explore uncharted territories, to solve the unsolvable. IBM's quantum-centric supercomputer is not just a new kind of machine, it's a new frontier, a new horizon that promises to expand the realms of possibility. It is the harbinger of a new dawn in computer science, setting the stage for an era where quantum mechanics is no longer the realm of theory, but the backbone of practical, problem-solving technology. Hold on to your seats because the quantum revolution has begun, and it promises to be a thrilling ride. IBM's quantum-centric supercomputer vision is a daring leap into the future, a glimpse at an epoch where the realms of classical and quantum computing cease to be disparate entities and coalesce into a harmonious computational synergy. It is a vision born of audacious dreams, indefatigable innovation, and the relentless pursuit of pushing the boundaries of what we believe to be possible. At the heart of this vision is the creation of a supercomputer so powerful, so advanced that it incorporates both quantum and classical power seamlessly, the same way today's computers integrate CPUs and GPUs. This concept is what IBM has christened quantum-centric supercomputing. The ultimate objective of this vision is to develop a 100,000-qubit quantum-centric supercomputer by 2033 that will empower humanity to confront and conquer its most pressing challenges. The quantum-centric supercomputer will be unlike anything we've seen in the world of quantum computing thus far. Its architecture will be an engineering marvel that expands our understanding of computer science and pushes the boundaries of quantum information theory. It's a new kind of beast, a powerhouse that has emerged from the nebulous realms of speculative theory and stands poised on the cusp of tangible reality. And this future-oriented vision has found its first tangible expression in IBM's Quantum System 2, revealed in late 2022. IBM plans to leverage multiple Quantum System 2s to create a powerful ensemble of thousands of qubits. This modular approach mirrors the flexibility and scalability observed in classical data centers, enabling the seamless integration of multiple quantum systems. The Quantum System 2 will serve as the building block upon which the 100,000 qubit supercomputer vision will be realized. But to truly appreciate the significance of this vision, one must grasp the inherent complexity of such an endeavor. To bring the quantum-centric supercomputer into existence, a comprehensive rethinking and restructuring of our approach towards both quantum and classical computing is required. This involves advancing the frontiers of engineering, conducting extensive research into fundamental physics, and challenging the existing boundaries of computer science and quantum information theory. Building a quantum-centric supercomputer of this magnitude is not a solitary endeavor. It necessitates a collective effort that harnesses the finest minds in the field. It is this understanding that spurred IBM to forge partnerships with leading academic institutions and research organizations across the globe. The University of Tokyo and the University of Chicago, two institutions recognized for their contributions to quantum computer science, quantum components, quantum algorithm design, and quantum communication, have become the first partners in this ambitious journey. Together, they are taking the initial steps to make 2033 the year of quantum-centric supercomputing. And beyond being a quantum leap in technological advancement, this vision also marks a shift in perspective. It underlines the growing understanding that classical and quantum computing are not adversaries, rather they are two halves of the same whole. Each has unique strengths, and the true power of computing lies in harnessing these strengths in a unified, integrated framework. This innovative perspective has formed the bedrock upon which the quantum-centric supercomputer vision rests. In essence, the vision seeks not only to build the most powerful computer known to humanity, but also to shift our very understanding of computing. It's about rewriting the rules, transforming the game, and challenging our collective imaginations to conceive of a future that is as inspiring as it is awe-inspiring. IBM's vision of quantum-centric supercomputing transcends traditional computational paradigms, nudging us towards an era where quantum and classical computing coexist and collaborate seamlessly. Two of the most vital elements propelling this vision are the innovative Heron processors and the groundbreaking Quantum System 2. The Heron processors are emblematic of the strides made in classical computing power. They represent IBM's cutting-edge classical processor technology designed to facilitate quantum computing's intricate processes, including complex control algorithms and error correction protocols. Heron is not just another classical processor, it's a pivotal instrument calibrated to accompany and complement the quantum journey. Now, quantum computing, unlike classical computing, deals with quantum bits or qubits, which can exist in multiple states simultaneously thanks to the unique properties of quantum mechanics. This concept, known as superposition coupled with quantum entanglement, endows quantum computers with unparalleled computational power. However, managing and leveraging this power requires tremendous control capabilities that classical computers struggle to provide. This is where Heron processors come into play. The Heron processor is designed to operate in the challenging environment of quantum computing, characterized by extremely low temperatures and high-speed computations. It embodies the symbiosis of classical and quantum computing, serving as the essential bridge that connects these two disparate realms. And while the Heron processors form the classical backbone, the Quantum System 2 is the quantum heart of IBM's ambitious vision. Revealed in late 2022, the Quantum System 2 is an engineering marvel that integrates thousands of qubits, making it an unparalleled quantum entity in the existing landscape. Building upon Quantum System 1's design, the Quantum System 2 provides a significantly improved quantum volume, a key metric used to measure quantum computer performance. Quantum System 2's robust design empowers it to operate within larger quantum networks while minimizing qubit error rates and extending qubit coherence times. The integration of the Quantum System 2 inherent processors is nothing short of revolutionary, creating an architecture that transcends the classical quantum dichotomy. This integrated system, the quantum-centric supercomputer, will leverage the Heron processor's classical processing prowess to manage the Quantum System 2's quantum capabilities efficiently. Both Heron and Quantum System 2 form the blueprint for the envisioned 100,000-qubit quantum-centric supercomputer. They represent the intricate dance of the classical and quantum world, showcasing the power that can be harnessed when these two distinct spheres work in harmony. But in this quantum revolution where quantum and classical computing join forces, a pertinent question arises. How do quantum computers measure up against the robust classical supercomputers of today? Quantum Utility, a collaborative experiment between IBM Quantum and UC Berkeley, answers this query convincingly, heralding a future where quantum computing emerges victorious. The experiment started with nerves running high and expectations being cautiously optimistic. Simulating the quantum experiment on some of the largest and most formidable supercomputers in the United States, including the Lawrence Berkeley National Lab and the National Energy Research Scientific Computing Center, the team sought to understand whether their quantum processor could generate reliable results. Rather than viewing this as a competition, the goal was to push their quantum device to its limit, to challenge conventional methods of computation, and to validate the accuracy of their quantum processor. And by leveraging some of IBM's novel error mitigation techniques, the experiment surpassed all expectations. Astonishingly, the quantum device not only matched the exact classical results, but also outperformed approximate classical results when the exact answer was available. Even as the team moved to circuits beyond the reach of classical methods, the quantum device continued to display unprecedented reliability. And so on one hand, IBM has made significant progress on the issue of scale. On the other hand, dealing with noise, a different problem altogether, required a novel approach. Quantum computers are notoriously sensitive to noise, disturbances that cause computational errors. But through years of relentless effort, IBM has developed error mitigation methods that can effectively filter the effects of noise from quantum computations. Such a leap was only possible due to the construction of a reliable quantum system of an unprecedented scale, the 127-qubit device with high coherence times. And what's fascinating about this quantum utility is the demonstration of quantum computation's prowess. The experiment turned up the noise, testing the accuracy of classical supercomputers against the quantum one. Surprisingly, the error mitigation techniques used allowed the quantum computer to match, if not surpass, the accuracy of classical supercomputers. Now, in the realm of quantum computing, collaboration plays a significant role as progress requires a collective effort of brilliant minds across multiple disciplines. To successfully construct the quantum-centric supercomputer, IBM recognized the need to join forces with world-leading academic institutions and research organizations. And the first steps on this path have led them to form partnerships with the University of Tokyo and the University of Chicago. Both these universities are renowned for their groundbreaking research and advancements in the field of quantum computation, including the design of quantum components, quantum algorithm development, and quantum communication. By pooling together their unique knowledge, skills, and resources, these partnerships aim to propel the development and execution of the quantum-centric supercomputer. The expertise from the University of Tokyo and the University of Chicago is expected to accelerate the realization of IBM's ambitious 100,000-qubit vision by addressing the multitude of complex technical challenges that arise. The University of Tokyo, known for its cutting-edge research in quantum mechanics, can contribute to the refinement of quantum components and quantum communication technologies. Similarly, the University of Chicago, with its robust computer science program, can help in the design and optimization of quantum algorithms and quantum information theory. This collaborative approach reflects the understanding that the world's biggest problems require global solutions. It also represents a concerted effort to advance scientific knowledge for the benefit of humanity. The journey to making 2033 the year of quantum-centric supercomputing requires not just innovation, but collaboration, and these partnerships embody just that, marking an important step towards an exciting quantum future.